In the name of God, Fundamental of Thermodynamics. Chapter 10, Irreversibility and Availability. From Borknack and Sontag, 7th edition. We now turn our attention to irreversibility and availability, two additional concepts that have found increasing use in recent years. These concepts are particularly applicable in the analysis of complex thermodynamics systems for with the aid of digital computers. Irreversibility and availability are very powerful tools in design and optimization studies of such systems. At first section we have available energy, reversible work, and irreversibility. And irreversibility. In the previous chapter, we introduced the concept of efficiency of device. Such a device such as turbine, nozzle, or compressors, perhaps more correctly termed in first law efficiency, since it is given as the ratio of two energy terms. We will now in the chapter 9 we talk about the efficiency of device such as turbine, nozzle, or compressor. First law efficiency. Given the ratio of two energy terms. We will now develop concepts that include more meaningful second law analysis. Our ultimate goal is to use these analyses to manage our natural resources and environment better. Our ultimate chapter analysis use to manage our natural resources and environmental better. Environment better. We first focus our attention on the potential for producing using useful work from some source or supply. We first focus our attention to potential for producing useful works. Consider the simple situation. Producing Consider this picture. Consider the simple situation shown in the part A. In which there is an energy source Q as shown here. Part A, energy source Q in terms of heat transfer from a very large and therefore constant reservoir temperature at T constant. What is the ultimate potential for producing work? This is the main. To answer this question, we imagine that a cycle heat engine is available as shown in part B. To convert the maximum fraction of Q to work, part B assume a heat engine to convert the maximum fraction of Q to work requires that the engine be compressible to completely reversible. That is a Carnot cycle, and that the lower temperature reservoir be at the lowest temperature possible. Often, but not necessarily at the ambient temperature. From the first and the second law for the Carnot cycle and the usual consideration of all the heat transfers as positive quantities, we have this relation for the Carnot, assuming a Carnot cycle as this picture. So to have what is the ultimate work can be taken from the heat transfer. For example, we assume a Carnot cycle here. The first law tells us that of heat engine equals to the minus Q0. For the ideal gas, the Thermodynamics temperature scale said that we have this relation, so we can obtain Q substituting to this relation. We can obtain the W reversible for this heat engine, T0 on T. We may say that the fraction of Q given the right side of equation is the available portion of the total energy quantity Q. To carry this so one step further, consider this situation shown in TS diagram as this picture. The total shaded area is Q. The portion of Q that is below T0, the environmental temperature, cannot be converted into work by the heat engine and must instead be drawn away. This part below T0 unavailable energy or cannot be converted into work. to work by the heat engine and must be thrown away. This portion is therefore the unavailable portion of total energy Q. Unavailable portion of total energy and the portion lying between the two temperatures T and T0. This part is the available energy part, for example. Let us next consider the same situation except that the heat transfer Q is available from a constant pressure source. For example, a simple for a constant pressure source simple heat exchanger as shown in this picture, or in this picture. Let me analyze this for constant pressure source, for example heat exchanger. Consider this picture. Constant pressure heat exchanger shown in this picture. There is a fluid in and fluid out. The Carnot cycle must be replaced by a sequence of such engine with the result in the part B, the PTS diagram. The only difference between the first and second example is that the second includes an integral which corresponds to the delta S So we have substituted in the first law. The first law say that Q minus Q0 equals to T0 delta S. In this case, the reversible work equals to Q minus T0 delta S for constant pressure source. Note that this delta S quantity does not include the standard sign convection. It corresponds to the amount of change of entropy as shown in this picture. Let me delta S quantity does not include the standard sign convention. It corresponds to the amount of change of entropy to the amount of change of entropy as shown in the picture. Delta S. Then the equation delta S specifies the available portion of the quantity Q. The portion are available for producing work in the circumstances below T0 in the picture here. Unavailable work in the constant pressure heat exchanger. In the preceding paragraph, we examined a simple cycle heat engine receiving energy. We will now analyze a real irreversible process occurring in a general control volume. Consider the actual control volume in the picture for a irreversible process. Consider the actual control volume shown in the picture with mass and energy transfer including storage effects. We have m dot I, for example, here m dot E, inlet outlet work out, Q in at temperature Tj, that affects the mass storage, energy storage, and also the entropy storage of the control volume with the generation of entropy. So we can have three equations: continuity, equation, in rate form say that the change of mass of control volume equals to the summation of m dot I minus summation of m dot E. The energy equation or second law, first law, tell us that heat in minus m dot I H total I. We have a definition for H total in previous chapters. It is a contain also the potential and m dot E minus W dot and entropy equation second law say that the change of entropy of the system at the temperature of the reservoirs exit entropy, inlet entropy plus A star generation we wish to establish a quantitative measure in energy term of extent or degree to which this actual process is irreversible. This is done by comparison to a similar control volume that only includes reversible process. So I will aim to establish a quantitative measure in energy term of the extent or degree to which this actual process is irreversible. This is done by comparison to a similar control volume that only includes reversible process. A similar control volume that only includes reversible process. Which is the ideal counterpart to the actual control volume. To the actual in as many aspects as possible. As many aspects as possible. it has the same strange effects. Left hand side of the equations, the same heat transfer. So in comparison we have the equation for continuity. We have same storage effects. The same heat transfer. And temperature, and the same flows of mass dot I and dot E at the same stage, so that the first four term in the generation term is 0. For the previous relations, we have the same first two for the same state and same Q, and for ideal and also real processes, we have same quantity of 4 parts into energy and entropy equation, and there is also difference, only difference between the last part, the actual work and actual entropy generation. In the ideal cases, the last term is substituted by the reversible positive flux of entropy delta S generation is equals to Q0 reversible on T0. What is T0 and Q reversible? And the only reversible process that increase entropy is heat transfer E. So we allow the one Q0 reversible from the ambient at T0. This heat transfer must also be present in energy equation for the ideal control volume together with the reversible work term, root of which replaces the actual work term. Comparing only the last term in the two equations, W dot control volume and S dot generation, for the actual control volume to the similar part of equation for the ideal control volume gives this relation to us that W dot control volume actual W dot reversible. From the equality of the entropy, we have and the reversible work W dot reversible is W dot control volume actual plus Q dot reversible. Zero. Notice that the ideal control volume has heat transfer from the ambient, even if the actual control volume is adiabatic, and only if the actual control volume process is reversible is this heat transfer zero and two control volume identical. To see the reversible work as a result of all the flows and fluxes in the actual control volume, we solve the entropy generation equation. Plus a start generation. And substituting to this relation and with result to the equation, then we can write this relation. At first we have W dot reversible equals to W dot control volume actual plus reversible. We have W dot reversible from the energy equation is if we make a correction here, S I S E, and for energy we have minus dE control volume of dt. And also should be equals to the this is W control volume actual, and we should T0 Q0 reversible and T0 delta S start generation. The start generation can be obtained from the entropy relation minus plus we write again, we have ES minus control value on DT So we have a expression for W dot reversible sigma Qj plus the m dot energy or entropy through flow T0 Si m dot E H total E minus T0 Se dE control value on dt minus the contribution from the heat transfer appears to be independent, each producing work, and the heat transfer go to a Carnot heat engine with low temperature T0. Each flows make a unique contribution, and the storage effect is expressed in the last parenthesis. This result represented the theoretical upper limit for the rate of work that can be produced by a general control value, and it can be compared to the actual work and thus provide the measure by which the actual control value system can be evaluated. The difference between the reversible work and the actual work is called reversibility. Difference between reversible work and actual work. I equals to irreversibility. As and since they represent the difference between what theoretically possible and what actually produced, is also called the lost work. Please note that energy is not converted, is not lost, energy is converted, and the lost work is a lost opportunity to convert some other form of energy into work. We can also express the irreversibility in a different form. Irreversibility reversible minus W actual. And also equals to a start generation. From this we see that irreversibility is directed proportional to the entropy change irreversibility. Directly proportional to entropy generation. Start generation, and this requires what is expressed in energy units because this requires a fixed and unknown reference temperature T0 to be generally useful. Notice how the reversible work is higher than the actual work by the positive irreversibility. If the device is like a turbine or the expansion work in the piston cylinder of an engine, the actual work is positive out and the reversible work is then larger. So more work could be produced in a reversible process. On the other hand, if the device requires work input, the actual work is negative, as in a pump or compressor. The reversible work is higher, which is closer to zero, and thus reversible device requires less work input. This is illustrated in the picture here, and it was described. It was for expansion work. Piston or cylinder or turbine. The actual work is positive and the reversible work is then large. So we have an irreversibility in the process and in the pump and compressor. So if we want to return to the first position, we need irreversible work higher than the actual work used. And this is for the case 2, the compressor and pump, the reversible work is higher, which is closer to 0, and the actual work is negative. And as the reversible device requires less input. The subsequent example will illustrate to the concept of reversible work and reversibility for the simplifying cases of a steady-state process, the control mass process, and the ambient process. The situation are all special cases of the general theory shown above. Here. The next section is the steady-state process, available work,